All right, so now we're going to talk about some reactions of benzene derivatives. And particular, this lecture is going to focus on reactions that take place at the benzylic position. So what the heck does that mean? Remember that we had, it's sort of analogous to an allylic carbon. Remember that when we had a double bond, something like this, we said that these positions are called allylic. Well, when you have a benzene ring, those positions, those analogous positions located just one carbon outside of the ring are called benzylic, okay? So these would be the benzylic carbons of this compound. Okay, benzene rings themselves are, like we said, remarkably stable. They're not easy to oxidize or reduce, right? So if you're trying to stick an oxygen on there or reduce it to a cyclohexane, it's very hard to do. However, the benzylic position is quite reactive. So let's take a look at this reaction here. Notice that I have this oxidizing agent here. Anytime you see chromium, think oxidizing. Chromium's a big oxidizer. So what it does is it oxidizes this benzylic position all the way. It's a strong oxidizer, meaning it goes all the way to a carboxylic acid group. Notice that it, in the process, chops off this back half, right? Completely chops that off. So you have a reaction at the benzylic position to create benzoic acid. And this will be the case as long as you have one benzylic proton, right? Or one proton on that benzylic position. If you have a quaternary carbon, meaning that it's bound to 4 other carbons, there is no oxidation reaction. We don't have to know the mechanism for this one, but just note that that proton is playing a key role. Okay. You can also accomplish the same thing with a different set of reagents. This one is potassium permanganate. Okay, but accomplishes the same thing. You have oxidation at the benzylic position all the way to a carboxylic acid group. Okay, talking about another reaction now. So that gets us, that's the oxidation of the benzylic carbon. NBS, remember we learned about this at the very end of last semester, and I told you that when you think NBS, you think allylic, right? And because that's what NBS does for us. When we first saw it, so the first type of reaction we would have seen would have been reacting something like this with NBS and heat, and it brominates that allylic carbon. Same thing with benzylic compounds. NBS will brominate the benzylic carbon. So by adding SBS or NBS, I put a bromine in that benzylic position. Okay. When you have benzylic bromides, they will react just like other alkyl halides do, right? So in this, this would be from chapter 7 type stuff. They react in a very similar manner. If you have a tertiary alkyl halide, it likes to undergo those SN1 type reactions in the presence of a weak base, right? If you have a primary, it will undergo SN2 type reactions in the presence of a good nucleophile like hydroxide. And so there's really no special thing that the ring is doing for you other than it's kind of just behaving like a normal primary alkyl halide or a tertiary alkyl halide. And similarly with our elimination reactions, right? If we had a tertiary alkyl halide and we had a really strong base, like this ethoxide ion, we wouldn't get any substitution. We would instead get elimination. Same if you had, remember starting with an alcohol group, we can dehydrate using a strong acid. These form, the elimination products are favored when there's competition between that and substitution, because you form a nice network of conjugated double bonds, right? Basically the new double bond that's formed can conjugate with that ring.